Hello, this is Dr. Calbreth, and we're taking on Chapter 3 in the Chemistry 2 textbook. Today we're going to be talking about chemical reactions. What we'll do is look at the idea of a chemical reaction. What are they? Define reactants and products. Then take a look at chemical formulas and see how to do calculations with them. Look at stoichiometry, which is a long word for balancing equations, and we'll talk about how to balance equations. And then we'll talk about the stoichiometric coefficient and its role in balancing equations. So let's leap right into this. Chapter 2 covered the idea of ionic and covalent bonds and looked at the two different types of bonds that hold atoms together to form molecules. Chapter 3 takes a look at reactions that lead to bond formation and breaking. After all, that's what chemical reactions are all about. And we'll see how to calculate how much material we need and how much we expect to get in a chemical reaction. Now here's a typical chemical reaction. We have the reactants on the left-hand side. We always write the reactants on the left-hand side of the arrow and the products on the right-hand side of the arrow. That's just a standard way of doing things. In this case, we have two reactants, acetic acid and sodium bicarbonate. Acetic acid is in vinegar, sodium bicarbonate is in baking soda. And we have a reaction where a hydrogen from the vinegar replaces a sodium ion on the baking soda, and what we get are products. We have sodium acetate, which is a salt that stays in solution. We get carbon dioxide, which is a gas and will bubble away. You can watch this fizz. And we get water. So what we've done is move materials around and come up with new materials. Now, stoichiometry involves the measurement of components, what's in there and how much. Tells how many of each kind of molecule is needed and how many of each kind of molecule is obtained as a product. It's very important if you're running a chemical manufacturing business, so you'll know how much of each reactant to buy and how much product you expect to get as a result of the reaction. Stoichiometric coefficient is simply the number in front of each kind of molecule. If there's just one molecule in the reaction, then you don't put a number. You don't put 1. But if there are 2, 3, 4, whatever number of molecules, you put that number. Now, the number of atoms always stays the same. You cannot create new atoms, nor can you destroy, take away, go hide old atoms. The number of atoms on the right-hand side equals the number of atoms on the left-hand side. So here in this case, we find in the two reactants, we find 2 carbon atoms in the acetic acid, we find 1 in the sodium bicarbonate for a total of 3. In the products, we find 2 carbons in the sodium acetate and 1 in the carbon dioxide for a total of 3. So we have 3 atoms of carbon and reactants and 3 atoms in the product. And we can do the same thing with hydrogens, with oxygens, and with the lone little sodium ion. We come out with 5 hydrogens on the reactant side, 5 hydrogens on the product side, 5 oxygens on the reactant side, 5 oxygens on the product side, 1 sodium each side. The law of conservation of mass. In a chemical reaction, atoms are neither created nor destroyed, only rearranged to make other molecules. So we can't come up with 5 atoms on one side and 3 on the other side, or 2 on one side and 6 on the other side. You have to have the same number of atoms on both sides of the equation. Now, if we look at this equation, we find a reaction between oxygen and hydrogen, and we know this reaction takes place and we form water. But what's the matter with the reaction? What's the matter with the equation? We have 2 oxygens on the left-hand side, we only have 1 oxygen on the right-hand side. Now we do have 2 hydrogens on either side, but you got an imbalance in the number of oxygens. So how do we fix it? Well, we change the stoichiometric coefficient. And by that we put numbers in front of the materials, in front of the molecules, so that we can indicate how many we have. Now note that when you're using the coefficients, you don't put a parentheses around them, and you don't put a 1 by the hydrogens up on top. But if we said we have 2 H2s, we have 2 H2 molecules, or 4 hydrogen atoms. 3 H2s is 3 H2 molecules, or 6 hydrogen atoms, and so forth. So if we get playing around with this and we say, okay, let's have a hydrogen and 2 oxygens. We have 2 hydrogens on each side, that works, but we have 4 oxygen atoms on the left side and only 1 on the right side. So that's an unbalanced equation. Now, how about we do this? We have 2 hydrogens, 2 hydrogen gases, H2 molecules on the left-hand side, with 1 oxygen molecule, or 2 oxygen atoms, and we get 2 waters. So we would write 2H2 plus O2 gives 2H2O. We'll note that we have 4 atoms of hydrogen on both sides, and we have 2 atoms of oxygen on both sides. So this is what we would call a balanced equation. Now, the other thing that we can do is calculate mass. If we want to know how many moles of something that we want to add, and we can tell that from the equation. The equation that we just looked at had 2 moles of hydrogen reacting with 1 mole of oxygen. Well, we're not going to count out 6.02 times 10 to the 23rd particles. We don't have a magnifying glass that big. We don't have tweezers that small, and it would take forever to do this. So we express a mole of atoms, say it weighs the same in grams as its atomic mass in atomic mass units. So 1 mole of hydrogen is 2 atoms of hydrogen. The atomic mass would be 2, so that would be 2 grams of hydrogen in the equation. So if we're using water and we want to know about water, 1 mole of water equals 2 grams of hydrogen plus 16 grams of oxygen, or 18 grams of H2O. 18 grams of H2O would contain 6.02 times 10 to the 23rd molecules of water. In the same way with acetic acid, you can follow the calculations there. 4 hydrogens, 2 carbons, 2 oxygens gives 60 grams per mole of acetic acid. Now, this is a way to do this if you make sure that you count everything up right. Calculate the molar mass, in this case, of calcium bicarbonate. And there's the formula for calcium bicarbonate. So you write out each atom. The calcium, there's 1 calcium, and it has an atomic weight of 4.08. So that's 40.08 grams per mole. Hydrogen, 2 times 1.01 from your periodic table. Carbon, 2 times 12.01. Oxygen, 6 times 16. So you multiply these out, and you get the grams per mole for each atom. You add them up, and the molar mass of the calcium bicarbonate is 162.3 grams per mole. This gives you a good way of checking your answers and making sure that you didn't leave anything out. Okay, calculate the number of grams of lead in 12.4 moles of lead. A little bit different kind of a problem, but we have 12.4 moles of lead divided by 207.2 grams per mole. How do we know that? We look on our periodic table and we find the atomic weight for lead. So that we come up with 2.57 times 10 to the 3rd grams of lead in 12.4 moles. Now, an easy way to double check this is to see that the units cancel and you're left with grams. So the moles cancel out. The units that are left over are grams, so you know you set the problem up correctly. Okay, calculate the number of moles of chloroform in 198 grams of chloroform. A little bit different way to look at the problem. Molar mass of chloroform is 119 grams per mole, 1 carbon, 1 hydrogen, and 3 chlorines. So 198 grams divided by 119 grams per mole gives us 1.66 moles. Now you notice that the grams cancel and what you're left with moles. Okay, let's take a look at types of chemical reactions. We can classify them in 4 basic types of reactions. The combination reaction, where 2 molecules go together to form a larger molecule. The reverse of that, the decomposition reaction, where a molecule breaks down into 2 or more smaller molecules. Displacement, where one molecule bumps a part of another molecule off. And the exchange, where molecules swap parts and end up with new compounds. Okay, here's some examples. Combination reaction, sodium metal and chlorine gas gives sodium chloride. So this takes the sodium atoms and the chlorine molecule, and you combine the two to form sodium chloride. This, by the way, is a pretty violent reaction. You don't want to do this at home. Decomposition, if you run electricity through water, you'll form oxygen gas and hydrogen gas. So the water molecule breaks down into 2 smaller materials. Displacement, sodium and water. The sodium atoms displace a hydrogen. You form sodium hydroxide and hydrogen gas. This is a little dangerous too. It gets hot and the hydrogen gas can ignite. Exchange reaction, hydrogen chloride and sodium hydroxide swap pieces and you form water and sodium chloride. So they have simply swapped parts of their material. All right, chemical reactions occur when bonds between atoms and molecules are created or destroyed. Okay, things go together, they form chemical bonds. Things come apart, you break those chemical bonds. In a chemical reaction, the reactants are converted to products. This is a standard language. Chemical reactions are written using chemical formulas. The reaction is represented by a chemical equation. Reactants on the left, products on the right. In a balanced chemical equation, the number of atoms of each element has to be equal on both sides of the equation. You can't lose atoms, you can't create them. Chemical reactions obey the law of conservation of mass. Chemical reactions are balanced using stoichiometric coefficients. We can calculate how much reactant is required and how much product will be produced by using a balanced chemical equation. And that's it. Thank you for coming, and I'll talk to you later.